Hi, my name is Dr. English and welcome to Periodic Table. Today we're going to be looking at individual groups and talking about the properties of those individual groups. Specifically, we're going to be looking at Group 1, which is the alkaline metals, Group 2, which is the alkaline earth metals, Groups 3 through 12, which represent our transition metals, Group 13, the Boron Group, Group 14, the Carbon Group, Group 15, the Nitrogen Group, Group 16, the Oxygen Group, Group 17, more commonly known as the Halogens, and finally Group 18, the noble gases. So before we get started, let's take a look at our periodic table and just identify one more time where do we find the metals, where do we find the nonmetals, and where do we find the metalloids. Starting at the top of the periodic table, the first thing that you need to realize is that hydrogen right here, while it is affiliated with Group 1 primarily because it has one valence electron, hydrogen is a non-metal, most definitely a non-metal. It is a reactive gas, it is colorless, it does not have any characteristics of metals, so that's why you see it separate from the rest of Group 1. So hydrogen, definitely a non-metal. The next thing that we need to do is just identify in general where the metals are located. And the metals are found on the left-hand side of the periodic table. So starting with Group 1 and Group 2, which is our most metallic elements, and going over past our transition metals, which we've talked about before, and up around polonium, and tin and gallium, those are all metals. Aluminum is considered a metal. And going back over through here, these are all metals. Also including our actinide and lanthanide series, which we find at the bottom. Don't want to forget those. Metals. When we talk about metallic properties, we're talking about all these elements. So the majority of the periodic table are found as metals. Now our metalloids are those that have both characteristics of metals and nonmetals, and those will include boron and silicon and arsenic and tellurium, going down through here, and antimony and germanium, and back up through here. So those are our metalloids. Then we have our nonmetals, and for the sake of this right now, we're just basically going to say that our nonmetals are all the way through here. And then finally, our noble gases, which also have nonmetal properties, are right here. And that is the way that New York State divides these up. So again, we have our metals, our metalloids, our nonmetals, and our noble gases. Let's start out by talking about Group 1. And Group 1 are the alkali metals. The Group 1 metals are our most reactive metals. They only have one valence electron, which we can see right here as we go down the group. All the electron configurations are going to end with the number 1. They lose electrons to form positive ions, and we could see that right here, all in the upper right hand corner. As we go down the group, we can all see that they have a +1 ion because they're all going to lose that one valence electron when they become ions. They're never found alone in nature. When we learn about chemical bonding, which is our next unit, we're going to realize that our Group 1 metals are going to be part of what we know as ionic compounds with nonmetals, and we're going to learn that in a little bit. They have low ionization energies, they have low electronegativities, increased reactivity as one moves down a group, and Group 1 is more reactive than Group 2. The final thing that I just want to say about Group 1 is that these are our most metallic elements on the periodic table. Now let's talk about the Group 2 metals, the alkali earth metals. These are going to be less reactive than Group 1. They have 2 valence electrons, and again, if we look at the electron configuration, we can see that they end with the number 2 as we go down the group. They're going to lose electrons to form positive ions. All of these have positive ions affiliated with them, and they're going to lose those 2 valence electrons to have a +2 charge, which we see right here, and that holds the same through the entire group. These can be found in nature by themselves. They're going to react with air pretty quickly to undergo something known as oxidation, which we'll talk about later. These have low ionization energies, low electronegativity values, and of course we can always go to Table S to confirm this general trend that as we go down the group from beryllium all the way down, we'll see a decrease in ionization energy and a decrease in electronegativity. Groups 3 through 12 are known as the transition metals, and we've talked about the transition metals before. These are metals with multiple oxidation states. In other words, if you look at something like manganese or molybdenum or titanium right here, they're going to have multiple positive charges associated with them. And that's one of the big things that we need to realize about the transition metals. Some of these will only have one oxidation number associated with them. And the most common ones that we identify are zinc with an oxidation number of +2 and silver with an oxidation number of +1. Typically, these are hard solids with high melting points. They're definitely less reactive than the metals in groups 1 and 2. We know these as the coinage metals because many of these metals will make up the currency that we use in our coins. One of the other things that you need to realize is that these elements are going to form ions that are associated with color in aqueous solutions. When we get into chemical bonding, in case you happen to look back at this particular video, is that the charge of these transition metals in an ionic compound must be identified by a Roman numeral. I say this now as just a reminder to you that someday down the road, when you do form chemical compounds and you use one of these transition metals, and it does have multiple oxidation numbers affiliated with it, when you name it, you're going to need to use a Roman numeral. Now let's talk about group 13. And group 13 is known as the Boron Group. The characteristics of these groups is these are all metals with the exception of boron, which is a metalloid. They have 3 valence electrons and will form +3 ions. So all of these here will end in the number 3 as we see right here, and all have a charge of +3 down the group. An interesting thing as you look at these visuals, which came off of periodictable.com, is that boron can definitely be identified as a metalloid. It's shiny, but it looks sort of brittle. When you look at aluminum or gallium or indium or thallium, these are your characteristic metals. They're malleable, they're ductile, they'll conduct electricity. You could definitely pound it into a thin sheet, so definitely having metallic properties. We've looked at trends in the past on a group of increased metallic character, and one of the things that we're going to notice now as we get into the metalloids and the nonmetals is an increase in metallic character as you go down the group. Now let's talk about group 14, the carbon group. All the elements in group 14 will have 4 valence electrons. So if we look at the end of their electron configurations, we can see that they all end in the number 4. Carbon is the only non-metal in this group. The pure elemental form of carbon can exist in different allotropes, such as diamond and graphite. Or fossil fuels like coal, petroleum, natural gas are all composed of carbon. Silicon and germanium are the metalloids. And finally, tin and lead are the metals. So if we look at this trend going down the group one more time, we have carbon, which is our nonmetal, silicon and germanium, which are our metalloids, and tin and lead, which are our metals. Then we have group 15, which is the nitrogen group. The characteristic of group 15 is that they will all have 5 valence electrons and commonly will gain 3 electrons to get a full octet in their outermost valence shell. Now we're starting to see the trend as we move from nonmetals to metalloids to metals of that whole act of now gaining electrons. So our elements at the top are more likely to gain electrons than lose electrons. Nitrogen and phosphorus are both nonmetals. Nonmetals, we see that increase in metallic character as we go down group 15, where we see our metalloids, and then finally bismuth and UUP at the bottom are metals. Let's talk about group 16, which is the oxygen group. These will have 6 valence electrons, so we will see the number 6 at the end of all these electron configurations. Oxygen has 2 primary allotropic forms, the first being diatomic oxygen, which is our elemental form of oxygen, which we need to survive, and the other one is O3, which is ozone. Also of note with group 16 is that they are going to commonly gain 2 electrons to get a full outer shell of 8 electrons as we go down the group. Oxygen, sulfur, and selenium are nonmetals, tellurium is a metalloid, and polonium is a metal. Group 17 is known as the halogens, and all the members of this group are nonmetals. They easily gain electrons. They do not exist in nature as individual atoms. They will exist as diatomics when bonded to themselves, and we'll talk about that more in our next unit. They have 7 valence electrons, so you can see that they all end in the number 7. They have high electronegativities, they have high ionization energies, and fluorine is the most electronegative and reactive nonmetal on the periodic table with an electronegativity of 4. At room temperature, fluorine and chlorine are going to be gases. Iodine is a solid and bromine is a liquid. And when we get to something known as intermolecular forces, we'll talk more about why that is. Let's finish this up by talking about group 18, which is the noble gases. And these are going to exist as monatomic molecules. And it's important to look at the word monatomic and understand what that means. The first part of the word is mono, so we know that as mono, which basically means one, and then atomic, which means atom. So exists as monatomic molecules or one atom molecules. In other words, they're really not going to bond with other elements. They have a complete outer valence shell of 8 electrons, with the exception being helium, because helium, as we know, is in period 1, which can have a maximum of only 2 electrons. They are chemically non-reactive, which we call inert. It's a common word that you need to know. The only exception is xenon and krypton, and under extreme environmental situations, they will react with fluorine. And that's why when we look at this particular group, we notice that krypton and xenon do have charges affiliated with them, and that's basically because of their interaction with fluorine and the fact that their valence electrons are so far away from the nucleus that they actually can form some types of bonds between themselves and fluorine. So what did we learn in this tutorial? Well, we went over the properties of group 1, group 2, groups 3 through 12. We talked about the boron group, the carbon group, the nitrogen group, the oxygen group, a little bit about the halogens, and finally wrapped it up with the noble gases. Need more help? Feel free to contact me. Have a great day.